Next, we consider a very simple property of pathwise connected. Obviously, if S1 and S2 are pathwise, I don't want to write so much. Pathwise connected, and they have no empty intersection. Then their union is also pathwise connected. Okay. This is very natural proposition. Intuitively, this is S1. This is S2. Given any 2 points in the union, we have several cases. These 2 points can be located both of them in S1, or both of them in S2, or one in S1 and the other in S2. For the first 2 cases, both in S1 or S2, we can use the pathwise connectedness of S1 and S2 to construct a path in the union. This path in S2 is also a path in the union, right? To connect these 2 points. So the general case is the case that a point is in S1, the other point in S2. How to construct a path joining these 2 points? The method is that because the intersection is not empty, we can take a third point C in the intersection. Then AC belongs to S1, and by the connectedness of S1, we can construct a path in S1 connecting A and C. And similarly, we can also using the pathwise connectedness of S2 to obtain a curve, a path connecting the path in S2 connecting C and B. So this gamma 1 and gamma 2, joining gamma 1 and gamma 2 together, we get a path joining A and B, right? But gamma 1 is a path from to S1, joining A and C. Gamma 2, similarly, a path in S2 joining C and B. How to write down the path joining A and B? I will tell you. The gamma can be defined in this way. Gamma T is gamma 1, 2T, for T in the first half of the interval. And gamma 2, T in the, how much? Okay. 2 minus T, 2 minus 2T. No. 2T minus 1. Okay, so you see this gamma, you can check that this gamma is continuous, and gamma 0 is gamma 1 0 is A, gamma 1 is gamma 2, take T equal to 1, so gamma 2 1, which is B. So this is the method to connecting two curves, right? Okay, I will not go to the detail. I suggest you to provide the detail. And okay, having studied the pathwise connectedness of subset of Euclidean space, we will study the properties of continuous function defined on such kind of subset. This is the generalization of the intermediate value property of the single variable continuous functions we studied in single variable calculus. Okay, the theorem. If D is pathwise connected, and F is a map from D to another Euclidean space Rn, which is continuous. Then the conclusion is that the image of this map, the image, I reminded you, this is a subset of Rm, right? So this subset of Rm is pathwise connected. Okay, so for the particular case, in particular, if m is 1, then f is a real value function on D and continuous. So fd will be a pathwise connected subset of the one-dimensional Euclidean space, which is the R, the set of real numbers. As we know, as we proved previously, any pathwise connected subset of R is an interval. So for the case m equal to 1, fd is an interval. So any continuous real-valued function defined on a pathwise connected set is an interval. The image of any such function is an interval. Okay, this is the particular case of this theorem. We prove this theorem. The proof is quite easy. For 2-point alpha beta in Fd, we want to prove that Fd is pathwise connected. Therefore, we need to show that given any 2 point in Fd, we can join these 2 points by a path contained in Fd. Okay, so by the definition of Fd, the image of a map, alpha and beta must be the image of some point in D. For this 2 point alpha beta, suppose Fa equal alpha, Fb equals beta. Here AB are points in D. Such AB must exist, maybe not unique. We can have several different A in D so that Fa equal to the same alpha. But they are not necessarily unique, but they always exist. Okay, so from the 2 point in the image of Fd, we get another 2 point in the domain of definition, our pathwise connect set D. Okay, we have AB from the set D, but D is pathwise connected. So by pathwise connectedness of D, we can find a continuous map which is a path in D joining A and B, continuous, such that gamma 0 is A and gamma 1 is B. So we find this path in D joining A and B. Our purpose, our aim is to find a path in Fd joining alpha and beta, but now we get the path in D joining A and B. How to get the path joining alpha and beta in Fd? Obviously, let capital gamma T, let capital gamma T to be F gamma T. That is to say, capital gamma is the composition of our map F and gamma and our little gamma. Okay, because our map F and the paths gamma are all continuous. So as their composition, this capital gamma is also continuous. And for this capital gamma, 0 is f little gamma 0, which is fa, which is alpha. Similarly, the value of capital gamma at 1 is beta. And the image of capital gamma, how about the image? I declare that the image of capital gamma is contained in Fd. Because, how to know this? Because the little gamma is a path in D. So, for t in 0, 1, gamma t belongs to D. And the f is d to Rm. So, capital gamma t is f gamma t. Since gamma t belongs to D, so f gamma t will belongs to Fd. Therefore, this means that gamma is a map from 0, 1 to Fd. So this capital gamma is a path in the image of our map Fd. And joining the given 2 points alpha and beta, we choose at the very beginning. So this proves that Fd is pathwise connected. So this proves our theorem. Okay. So to conclude this section, we introduce a terminology. A subset in Rn, we said that this subset has intermediate value property. This is a definition. What's intermediate value property? If any continuous function on D, if Fd is an interval, for any continuous function, real value function defined on D. So this is the so-called intermediate value property. So our previous theorem tells us that a pathwise connected subset of Euclidean space has intermediate value property. But if a set is not pathwise connected, can it has this intermediate value property? This is a natural question. We will see that this is also true. That is to say, pathwise connected is a sufficient condition for intermediate value property, but the converse is not true. There are some sets has this intermediate value property, but not pathwise connected. Okay. So this is the topic of our next lecture.